Welcome to the course Analysis of a Complex Kind. This is the first lecture in this course, and I'll introduce the course to you, tell you some of the topics we'll be covering, and give you a history of complex numbers. A little bit about myself. So my name is Petra Bonfert-Taylor. I was born, raised, and educated in Germany, more precisely in Berlin. I got my PhD at the Technical University of Berlin in 1996, and then I went for a postdoc at the University of Michigan. And after 3 years there, I started a tenure-track position at the Western University, where I'm now a professor. And I've been there since 1999. In this course, we'll be studying complex numbers and their properties. We'll go into details later. Just as a quick review, complex numbers have a real part x and an imaginary part y, and we often display them in the complex plane where x, the real part, is the x-coordinate and the imaginary part is the y-coordinate, and so this gives us a nice graphical interpretation of complex numbers. Don't worry, we'll review all this later. We'll also explore some of the history of complex numbers. We'll talk about some important people who were important in the development of complex analysis. We'll talk about Bernard Riemann. We'll talk about Cauchy. We'll talk about Weierstrass. We'll talk about all kinds of people. We'll also talk about the complex number I. Where did it come from? What is its history? We'll talk about limits. Where do those come from? Especially limits in complex analysis. We'll talk about the constant E. We'll talk about some topological concepts, such as open sets or connectedness. We'll explore all of these in this course. Once we have studied complex numbers for a little bit, we'll be able to learn about complex dynamics. You'll probably have seen this beautiful Mandelbrot set or zooms into the Mandelbrot set before. We'll be able to learn how to construct this beautiful set and how to calculate it. This is an example of a Julia set over here, and we'll also learn how to create those. So this is the Mandelbrot set, and here's an example of a Julia set, and we'll study both these in this course. After having learned about complex numbers, we'll study complex functions. We'll understand what it means for a function to take a complex argument, to plug in something complex into a function, and for the output to be complex. We'll study their continuity, complex differentiation. So if you're talking about a function that takes a complex argument, in the picture that we saw on the first slide, we realized that a complex number can be displayed as having a real part and an imaginary part. So there was the x and the y, giving us a complex number z. So in order to graph a complex function that maps a portion maybe of the complex plane into another portion of the complex plane, we're going to need two pictures, one for the domain and one for the image. So where does this get mapped to? So maybe this will get mapped to something like this. And we'll study how to graph complex functions and how to visualize complex functions. We'll be able to talk about some of the most important theorems in complex analysis, one of them being the Riemann mapping theorem. We won't be able to prove a theorem like that, but we will be able to study it. Here's what the Riemann mapping theorem says. No matter what shape domain you choose, if you choose some kind of figure that doesn't have any holes, you'll be able to find a mapping, an analytic function, one of these mappings we'll be studying in this course, and map it onto the unit disk. We'll explain this in detail and learn why this is an important theorem. We'll study complex integration. Since we'll be differentiating, we should also be integrating. So we'll study complex integration, and we'll learn formulas like this. These will all make sense to us after this course. And as a consequence, we'll be able to prove the fundamental theorem of algebra, for example. Given any polynomial, we're able to factor this polynomial into n factors. This is the fundamental theorem of algebra. We'll study power series representations of analytic functions. And we'll even be able to talk about the Riemann hypothesis, which is an open conjecture that was conjectured by Bernard Riemann and to this day has not been proved. And it is related to prime numbers, believe it or not. And we'll study how it is related to prime numbers, and the veracity of this conjecture has implications for the distribution of prime numbers. So let's get started and let's talk about a brief history of complex numbers. So let's look at a quadratic equation, something like x squared equals mx plus b. We all know how to solve a quadratic equations, and if you think about this briefly, the solutions are x is m over 2, where m is this number in front of the linear term, plus or minus the square root of m squared over 4 plus b. And if you look at this equation by itself, what it really represents is it represents the intersection of the graph of y equals x squared, and you see that graph right here, y equals x squared, and the graph of y equals mx plus b, which you see right here. Just a line. Mx plus b is just a line. And when are those two equal? Well, they're equal where the graphs intersect. So they're equal here and here in this particular picture. So these are the two x values that are given to you by this formula. So that was discovered a long time ago. The Greeks already knew this, and we're all very familiar with this formula. So here again, I just wrote down this formula for the solution of that particular quadratic equation we were looking at. But what would happen if this number under the square root right there, m squared over 4 plus b, was negative? Then you wouldn't be getting any solutions, right? So in particular, if your equation was x squared equals negative 1, so in that case, m, the linear term, is actually 0, and that b is equal to negative 1, so you would end up with a solution of x equals m was 0, so 0 over 2 plus or minus the square root of m is still 0 plus b, and b is negative 1. So, of course, we know that x squared equals negative 1. It has no real solutions. There is no number you can square and get negative 1. And it is often argued that this led to the invention of the complex number I, which is just the square root of negative 1. If there was a number whose square root is negative 1, then we could solve this equation, we'd be good. And that number is called I. And so it is often argued that the solution of the quadratic led historically to the invention of I. But historically, actually, there was absolutely no interest in non-real solutions of the quadratic equation, because in that case, it is simply the case that the graph of y equals x squared and mx plus b don't intersect. So for example, in the case x squared equals negative 1, while the graph of y equals x squared is just this parabola, the graph of the right-hand side right here is the line y equals negative 1, which is this line down here. And these two graphs simply don't intersect. They have nothing to do with each other. They never intersect. And so there is no intersection, so there's no solution. But we don't need to make up a complex solution. There was simply historically no interest in non-real solutions because the graphs just don't intersect. So where did complex numbers really come into importance? It is with the cubic equations. Those were the real reason for the importance of complex number. So let's look at a cubic equation. We don't have a quadratic term here. It's just an example of a cubic equation. So the cubic equation we'll be looking at is x cubed is px plus q. And again, a solution of this equation represents the intersection of y equals x cubed, and I drew that right here, with y equals px plus q, which is just that line right there. So again, it's the intersection of a curve and a line. And as we can see, because the cubic goes all the way from plus infinity to minus infinity, no matter what line you draw, it'll always intersect the cubic somewhere. There's no line you could draw that won't intersect this cubic. So this is very different from the quadratic case, which was a parabola, and you could draw lines that just don't intersect the parabola. In the cubic case, any line will intersect the cubic. So there always must be a solution. Now, Italian mathematicians Del Ferro and Tartaglia, followed by another Italian mathematician Cardano, showed that this cubic equation, x cubed equals px plus q, has a solution and is given by this rather complicated formula. So, p is the number in front of the linear term, q is that number that doesn't have any x's attached to it, And if you take these numbers and plug them into this rather complicated equation, then supposedly you get an x. So let's actually try this out. So go ahead and look at the equation x cubed equals minus 6x plus 20. What solution does this formula give you? Well, first we notice that what is p and what is q? P is equal to negative 6 and q is equal to 20. So when we plug these numbers into this equation right here, under the inside square root, we get q squared over 4, which is 100, minus p cubed over 27 is minus 8. So together 100 minus minus 8 is 108. So we find x is equal to the cubed root of the square root of 108 plus q over 2, so that's 10, minus the cubed root of, and now we have the same square root term right there, square root of 108, but then minus 10. Then you get your calculator out and you find out that the solution is x equals 2. And indeed, 2 cubed is equal to 8, and minus 6 times 2 is minus 12, plus 20, that is also 8. So 2 is indeed a solution of this equation. So far so good. That formula seems to be correct. About 30 years after the discovery of this formula, another Italian mathematician by the name of Bonfert-Taylor considered the following cubic equation. X cubed equals 15x plus 4. So p is equal to 15 and q is equal to 4 in the formula we just looked at. And so now if you plug it all into that formula, you find yourself with x equals the cubed root of 2 plus the square root of minus 121 plus the cubed root of 2 minus the square root of minus 121. And that's a problem because if you can't take a square root of a negative number, then this does not give you a solution. However, we know any cubic and a linear function, they must intersect, so there must be a solution. But you can't find it using this formula. So Bonfert-Taylor had a really wild thought. I had been talked about, and the square root of negative 1 being I had been talked about. And so he took this a step further and said, well, maybe if I could make calculations with this number I, the way I do normal calculations, maybe this ends up being some number that involves an I, and on the left-hand side some other number. Maybe things would cancel out, so I do end up getting a real solution. And he thought about this for quite a while and came up with a thought that the cubed root of 2 plus square root of negative 121 should be 2 plus the square root of negative 1, and the cubed root of 2 minus square root of minus 121 should be 2 minus square root of negative 1. Then when you add up these two terms, as you have to in that formula, 2 plus square root of negative 1 and 2 minus square root of negative 1, no matter what square root of negative 1 really is, it cancels out with this minus square root of negative 1. So these two terms will just cancel each other out, and what's left is 2 plus 2, which is equal to 4. 4 is the solution to that cubic equation we're looking at. It is the desired solution. Now, let's check this out. Is it really true that 2 plus square root of negative 1 cubed is equal to 2 plus square root of negative 121? Because that would have to be the case if it was indeed true that the cubed root of this number is 2 plus square root of negative 1. If the cubed root of the left-hand side is the right-hand side, then if I cube both sides of the equation, then the cube of the left-hand side, if I cube this side right there, I get this term. It should then be equal to the right-hand side without that cubed root. So this would have to be true. So let's check out that this is indeed true. What is 2 plus the root of -1? Quantity cubed. Well, that's tough because we don't really know how to work with the square root of -1, but let's just pretend all the normal rules hold. So how do you cube something? Let's remember the way to cube a plus b. The way that's typically done by a formula is a cubed, you can just FOIL it all out, but it's a cubed plus 3 times a squared times b plus 3ab squared plus b cubed. So if we use that formula right here, we would get 2 cubed plus 3 times 2 squared times the square root of -1 plus 3 times 2 times the square root of -1 quantity squared plus the square root of -1 quantity cubed. So what does that give us? Well, what is the square root of -1 squared? Even if we don't know what the square root of -1 is, if we square whatever it is, the square root and the square should cancel each other out. So this should really be -1. That's the idea of the square root of -1. When you square it, you get -1 back. And what is the square root of -1 cubed? Well, that's really the square root of -1 squared times another square root of -1. What we just figured out, the square root of -1 squared is -1, and then there's this extra square root of -1. And so altogether, let's simplify. 2 cubed is equal to 8. Then we have 3 times 2 squared, that's 12, times the square root of -1. And then we have 3 times 2 times -1. So 3 times 2 is 6, times -1 is -6. And here we have -1 times square root of -1. Now we can combine at least like terms. We can combine this 8 and this -6. 8 minus 6 is equal to 2. And we have 12 times whatever square root of -1 might be. And we're subtracting from that 1 times the square root of -1. So altogether we have 11 times the square root of -1. What is 11 times the square root of -1? Well, if square roots kind of interact normally even with negative numbers, then we might be able to pull that 11 inside the square root, and that becomes 121 on the inside. And so this should then be able to 2 plus the square root of -121. And that's what we wanted to show. And so Bombelli was indeed correct. If I take the cubed root of this right-hand side, the cubed root of 2 plus the square root of -121 is indeed equal to the cubed root of this left-hand side, 2 plus the square root of -1. And then similarly, when you replace this plus right here with a minus, then this plus also becomes a minus, and then we add those two terms up, you end up with that 4, which was the solution to the cubic equation we were looking at. And so all of a sudden, solving a perfectly real problem, that cubic equation Bombelli was looking at, required accepting that complex numbers are important objects and that we can do calculations with them as if they were objects that behave according to the rules of our real numbers. This is considered the birth of complex analysis. It showed that perfectly real problems require complex arithmetic for their solutions, and it also showed that we need to be able to manipulate complex numbers according to the same rules we're used to from real numbers, like the distributive law. And we need to be able to add them. We need to find out how to multiply them. So we need to study the rules of doing arithmetic with complex numbers. And that's what we'll study next.